Okay, good morning. Just a quick video here to answer some questions that I'd gotten from some students on Friday about Chapter 3, Section 2. And the first topic here is these conditional probabilities, probability of an event occurring given that some other event has already occurred. Conditional probability of event B occurring given that event A has occurred. And that's a phrase you'll see often in this textbook is given that event A has occurred, given that something has happened. That's a good clue that you have to look at the conditions that's going on. So we're going to look at example one. The first one here says two cards selected in sequence from the standard deck. Find the probability that the second card is a queen given that the first card is a king. So we're talking about the probability that the second card is going to be a queen. But we've already pulled a king out of the deck of cards. So we no longer have, now pulling a king out does not affect how many queens are in the deck, but it does affect the total number of cards in the deck. So whereas pulling a single card out of a deck is typically, if you're saying a queen, would be 4 out of 52, because a king has already been removed, then the correct answer for this, as we see here, is 4 out of 51. Since the first card, the king, was removed, the second card has only 51 choices instead of 52 choices. But what I really got a lot of questions on was these tables. So let's take a look at this. The table on the left shows the results of a study in which researchers examined a child's IQ in the presence of a specific gene in the child. Find the probability that the child has a high IQ given that the child has the gene. And since they give us that condition that says that given that the child has the gene, that tells us we only want to look at the ones that have the gene present. So we have this column here. This is called a two-way table. This column here that says the gene is present. Now I've copied this over here into a Google Sheet. So when it says given that the child has the gene, that means we're only going to be talking about these numbers right here. So those are the only numbers we're concerned with in this question. We want the probability of a high IQ given that the gene is present. So we're only looking at the children with the gene present. Well, we have 33 with a high IQ, and we've got 72 total with the gene. And that's going to be your answer. Now you could divide that and get a decimal. Equals 33 divided by 72. And there we go. And for the most part with this textbook, we're going to go to 3 decimal places, almost all of our probabilities, until we get to some more complicated ones later on where we're using normal distributions or binomial distributions. But for right now, 0.458, perfectly acceptable answer. And I believe that's what the textbook tells us right here. So let's jump down here to the try it yourself problem, which gives us 2 more examples. Find the probability that the child does not have the gene. And the key to that statement there is they did not give us any kind of a conditional. They simply told us find the probability that the child does not have the gene, which means we're looking at all of the students, all of the children in total. So finding the probability that the child does not have the gene, we want to look, how many total do not have the gene? 30. How many children total in the study? 102. Okay, they did not give us any kind of conditional here, so we don't have to worry about picking one column or the other. Probability the child does not have the gene means we look at all the children who do not have the gene out of all the children total. And the last question they ask us is find the probability that the child does not have the gene given that the child has a normal IQ. So we're looking only, they said, given a normal IQ. That tells us, we're going to unhighlight these because we're done with those. And what tells us now, given that the gene is normal, given that the normal IQ, tells us we're only looking at the normal IQs. So we're only going to worry about the numbers I just highlighted. How many normal IQs do not have the gene? 11. Out of how many normal IQs total? 50. equals 11 divided by 50. And that would be our answer, 0.22. So two-way table, conditional probability, look for that phrase given that, and keep in mind that when it says given that, whatever condition they give you, in this case it was given a normal IQ, meant only look at the normal IQs. Here it said given that the child has the gene, meant only look at the ones that have the gene. Okay, that tells you which group to look at and which total you'll be looking for. There's other questions that sometimes you might get a question that says, find the probability that a child has the gene and a normal IQ. Let me fix that alignment so we can see the whole question. Oh, there we go. Probability that the child has the gene and a normal IQ, and I just made this up off the top of my head. There's no given that phrase here. It wants the child to have the gene and have a normal IQ. Well, children with the gene and a high IQ, you're looking for the intersection of the column in that row, because both of those things need to exist. Gene present and high IQ, that's 33 students. Because they didn't give a conditional statement that told us to only look at one group or the other, we have to go out of the total here. So our answer to something like that, where it uses that word and there's no conditional statement given, means we're going to look at that intersection of the column in the row, and we're going to go out of the total. So we're going to use this number here for this one. We'll highlight it. And this one here. Okay, I hope that clears some of those up. Go down here, clear that, so you know where that came from. I hope that clears some things up. Other things in this section, independent or dependent events, pretty straightforward. This multiplication rule simply means that if multiple events are happening in a row, you take the probability of each event and multiply them. Two cards selected from a deck without replacing the first card. Find the probability of selecting a king and then a queen. So two things are happening. You're pulling out a king out of the deck, not replacing it, and pulling out a queen. Well, there's 4 kings in the deck out of 52 cards. So the probability of a king is 4 out of 52. Since you have not replaced that king, there's still 4 queens in the deck, but now there's only 51 cards to pull from because you pulled the king out already. So we're going to multiply those two probabilities together. Again, remember, multiplying fractions. Numerator times numerator, denominator times denominator. 4 times 4 is 16. 52 times 51 is 2,652. Divide those and get the answer. Now, if you did the division of each fraction individually, got 2 decimals and multiplied them, you would still get the correct answer. I caution you on that, because if you round those decimals off too much, you might end up with a decimal here that is rounded twice. We never like to round more than a single time in mathematics. So it's always better to do your multiplications in fraction form. And your calculators are smart. They can do that. You put parentheses around it. 4 divided by 52, close parenthesis, times parenthesis 4 divided by 51, close parenthesis. It will give you the correct answer. Calculators are smart like that. Coin is tossed and a die is rolled. So these are events that are independent of each other. So the coin toss is not going to affect the die roll. So what's the probability of, what does it ask for here? Heads and then rolling a 6. Probability of heads on a coin flip is 1/2. Probability of 6 on a die roll is 1/6. If we multiply those together, we get 1/12. So pretty straightforward stuff, the multiplication rule. I don't think there's any really complicated questions in here. Keep in mind, pretty straightforward stuff. If you have any questions, you can email me. If not, YouTube is your friend. There's lots of videos available out there. I posted some links to a couple things. Do your best. Get a hold of me if you have any questions.